Welcome to Plutus IAS, and today we are covering Born Haber Cycle. Now, Born Haber Cycle comes from your Thermodynamics unit from your paper 1. Now, why is it important? The thing why it is important is that before Born Haber Cycle, there was certain types of energies which cannot be calculated. And specifically in terms of Born Haber Cycle, we are calculating about your lattice enthalpy. Why lattice enthalpy is important? Lattice enthalpy is important because every different solid crystallizes in a different environment, and that environment decide what type of interaction with it is having. For example, if it's crystallizing in an octahedral environment, it will have octahedral splitting. If it is crystallizing in a tetrahedral environment, it will have tetrahedral splitting. So you can use lattice energy and you can also relate it with your coordination chemistry. But the thing is, lattice enthalpy cannot be calculated simply by knowing the structure, because it defines it, because a lattice enthalpy is determined by the structure, the arrangement, how the overall structure is being formed, what is the interaction that is having, what are the impurities. So before Born Haber cycle, no such thing ever existed. So Born Haber cycle is primarily based on two predefined notions. It is based on two notions, or you can say important laws. First one, that is the first law of thermodynamics. First law of thermodynamics. That means the total energy in a system can never be created nor be lost. It just can be transformed from one form to another. So that means if a lattice being formed from two individual species, whatever the energy they are utilizing for their combination to give you a particular solid, that energy will remain constant. Second, it is based on Hess law. Hess law of constant heat summation. Constant heat summation. For those who don't know what is Hess law of constant heat of summation, you can search it. We have already made a video prior to this regarding Hess law. Without Hess law, you won't be able to understand it, but in general, you can understand this. Hess law states that since enthalpy is a state function, enthalpy is a state function. Enthalpy is a state function. State function. So that means it is not dependent on the path from which it is being taken. It only depends on initial and final state of the system. So, example, let's say there is some species A, it is going to B, going to C, and then to D. It has some enthalpy delta H1, it has some enthalpy delta H2, it has some enthalpy delta H3. Now, what will be the enthalpy going from A to D directly? Well, this can simply be, since enthalpy is a state function, the initial and final state are same for the system. That means overall enthalpy would be the summation of all the enthalpies involving in different steps. So, and always remember, all state functions are additive in nature. They are additive in nature. Now, so Hess law suggests that no matter what happens, whether the reaction is taking place in multiple steps or in a single step, the total enthalpy of the system will always remain constant. Now, using these two notions, we can apply it towards your Born Haber cycle. So let's assume this is to be Na in solid form combining with Cl2, giving you NaCl type of lattice. Now I need to find what is the total amount of energy that is being required for the formation of this particular lattice. So what happens is, in general, I can assume this is your A plus and let's say B minus, an ionic solid. A plus ion combines with B minus ion to give you lattice AB solid. This is the most simplest way you can represent it. So, another thing. First, I need to convert A to the A in gaseous form. So for that, first I require my sublimation energy. Sublimation energy is an endothermic process, so you need to add it so that the A can now be converted to gaseous form. Then after the gaseous form, I need to ionize it so that it can form the A plus ion. For that, I will require ionization enthalpy. So that means conversion of A to A plus require two types of energy. Why? In case of B2, here I only required only one single B minus ion, so I am reducing energy to the half. So first I need to break down this B2 into a single molecule B minus. So I require total amount of energy to break one mole of bond and then to separate them from one another so that they do not interact. So for single B, I require half of the initial energy. And now it has become B in gaseous form. Here, you will provide it some electron affinity and then it will turn into your gaseous ion. When these two ions interact, there will be electrostatic forces that will stabilize it, and the total energy that will be thrown out will be your U, your lattice enthalpy. Now, using all these info, that means all the energies that are involved in this process, it should be that the enthalpy of formation for the AB crystal should be sublimation energy half of dissociation energy plus ionization enthalpy plus electron affinity plus lattice enthalpy. That will be equal. Now, since formation of a lattice will always be possible if the entire process is endothermic in nature. So that means, now sublimation, dissociation, ionization, enthalpy, these all are endothermic processes. That means they have the delta H value positive and this should be negative. So that means for any solid to be ever formed using Born Haber cycle, we can also define the set of conditions that are required for the formation of a particular solid, and you can also find the total amount of energy required for the formation of it. Since enthalpy can be calculated, but lattice enthalpy can't be calculated, using this entire equation and all the parameters, you can calculate the lattice enthalpy for that particular lattice, for the solid. So here, that both are negative energies because they are exothermics, it should always be greater in value, in magnitude, than the other type of positive energies. Only then we can say that the formation of a lattice is feasible. So that means Born Haber cycle also helps to define criteria for the formation of a particular solid, when it will form or when it will not form. Okay, so I hope this would have cleared all your doubts regarding your Born Haber cycle and you learned something new today. In case of any doubt, you can add it to the comment section, or any specific topic that you want us to make the video for, you can also add it to the comment section and we'll get back to you. Thank you for joining us for today. Till then, like, share and subscribe.